Welcome to speeding up quant analysis with multiple computers, multiple CPUs, multiple cores, and a discussion of those configurations. I will focus first on the biggest bang for the buck, which is using multiple computers to analyze at the same time. So the situation here is you have extremely large batches. An example of that would be target screening with a long list of compounds. All right, let's talk about parallel quant analysis. And what we've got here is a configuration with two computers, although this concept is not limited to two computers. I've got, let's say, a Z400 here and a Z400 here, and I'm a very fast backbone. I would suggest a local subnet to keep the traffic local. And I've got my data, which has been acquired on this shared disk. And what I'm going to do here, let's go through the steps, is first to acquire the data and then to analyze the data. Now, this scenario works when you can divide up your batch into two or more compound lists. So I'm going to say compound list A and compound list B, and there's some categorization, let's say by functional group, that allows me to report and think about the batch in terms of multiple compound lists. So here I'm going to basically be running two batches at the same time. And the goal here is the finishing time. So if I run two of them at the same time and they finish twice as fast, that's the bottom line. So batch for compound sublist A and then the batch for compound sublist B will be running against a shared data, one set of data on a shared computer. That's the bottom line. All right, let's take a look at the experiment. So this experiment compares running a batch on one PC versus running two batches on two PCs in terms of the finishing time. So you can see there really is very little difference between the finishing time of doing 1,000 compounds on one PC versus 1,000 on one and another 1,000 on two, sharing the data and finishing basically the same time. So let's take an example to see if we can see what this would mean. If I had to analyze 2,000 compounds, you would see it would take me over 250 minutes according to this graph with this particular data. Now, this graph is nonlinear. So if I were to actually organize it so that I could analyze that in 1,000 and 1,000 at the same time, two batches finishing, you'd see that I'd finish in roughly 80 minutes. So that's a difference of well over 3x in terms of the finishing time organizing with this dual computer configuration. Another idea that would come up is parallel processing. Most computers sold today are going to have multiple cores, and the idea is let's keep all those cores busy and we'll finish faster. That's not necessarily true. It depends upon the scenario. When we're back to memory contention and the locking of the shared memory resources, and the question is what scenarios fit with processes that can move ahead independently and proceed without waiting on another task. A scenario that really fits with multitasking is unknowns analysis, which is contrasted to what I call the sequential nature of quantitation, which has steps where you have to build the calibration table before you do target final concentrations. But in unknowns analysis, if you run that, you'll notice that the cores are all busy because deconvolution is running on each sample, as well as then library search and then target matching. So if you were to look at the task manager, you would see all the cores are busy, and that gives us about a 15% improvement in performance, significant. I'd like to add in a section here of R&D notes. We spent quite a bit of time in software working on fast projects which optimize performance and scalability. So other ideas which come to mind, one would be buying a honkin' computer like a Z800 which has dual CPUs in the same computer, and at this point 6 cores, and they're always adding more cores. And the question is, would this be faster? Well, what happens is you end up with memory contention, and the memory subsystem that's being used on a single computer is shared. So the caching environment and the nonlinear behavior we just saw in the previous is caused by memory contention happening as multiple cores try to access the same memory. And that would become a bigger problem on one computer than the example that I showed you first, which is to buy 2 separate, much lower cost computers and then to run them on the shared data. A couple of quick experiments to communicate. First, one that uses different disks with different cache sizes. And you'll see here that even if you buy 64 megabit cache for your disk, it doesn't really make a whole lot of difference even if you move up to 2,000 compounds. And another experiment shows that with this batch, this many compounds and samples, and acquisition size, mileage may vary, but in this case, moving up to 16 gigabyte in terms of the RAM in that computer really didn't show much difference than what was half of that. All right, thank you for your attention.